This is the third probability distribution model. We have looked at Bernoulli distribution, isn't it? Whereby this one you have only two possible outcomes. You either win or lose. If you toss a coin, you either get a head or a tail. You only have two possible outcomes. The event is binary. And again, we looked at binomial. We said that if we sum these Bernoulli events, the sum of Bernoulli events will give you a binomial random variable. Now today I want us to look at what is called Poisson probability distribution. This is a probability distribution that expresses the occurrence of events or the probability of events within a fixed time. The probability of events within a fixed time with known mean rate of occurrence or with known averages of occurrence. For example, if customers are arriving in a bank, let's say within 1 hour, the customers will be arriving in a bank, right? Within 1 hour. That one takes a Poisson distribution. The number of clients that arrive at a facility within 20 minutes, time now is 20 minutes, and you will be given the other average, then that one takes a Poisson distribution. The probability mass function, the PMF is given by Px is equal to x, which is equal to e raised to negative lambda, lambda raised to power x over x factorial. And x can pick on these values. It can be 0, 1, 2. It picks the values on a discrete time scale. 0 elsewhere. 0 elsewhere. So this is what is called the probability mass function. And we call it a probability mass function because it is a discrete random variable. Then we can also look at, we can verify whether it is a valid PMF, valid PMF. How do we do this? The sum of all probabilities from x is equal to 1 up to infinity or n, p x is equal to x must be equal to 1. Add all those probabilities. So this one is the PMF. So if you take the sum from x is equal to 1 up to 0 up to infinity or n, let's use n. Then the Px is equal to x is replaced by the probability mass function, that is e raised to power negative lambda, lambda raised to power x over x factorial. Now, we can factor out e raised to power negative lambda because it's a function of x. So we have e raised to power negative lambda. Summation from x is equal to maybe 0, let's say 0. 0 up to n e raised to power negative lambda, lambda raised to power x over x factorial. Now you look at this. This is a series. And this series is an exponential series. So this one is e raised to power negative lambda. Then you expand this series, you will have 1 plus lambda squared over 2 factorial plus lambda raised to power 3 over 3 factorial all the way to lambda raised to power n over n factorial. This series converges. This series converges at e raised to power lambda. The convergence of that series is e raised to power lambda. So e raised to power lambda negative lambda dot e raised to power lambda is e raised to power 0, which is equal to 1. And therefore, this is a valid PMF. Yes. To show that the expectation of a Poisson distribution is equal to the parameter lambda. How do we get the expectation of x is equal to summation from x is equal to 0 up to infinity x p x is equal to x. So this one is equal to, or you can set x is from x infinity up to that. So this one is summation from x is equal to infinity up to infinity, negative infinity up to positive infinity. X, we bring in the PMF, e raised by negative lambda, lambda raised by x over x factorial. Now the next step will factor out e raised to power lambda because it doesn't have the function x. Yes. So you get e raised by negative lambda, summation from x is equal to we cannot sum from x is equal to 0. If we sum from x is equal to 0, the whole of this thing will be equal to 0 because of this x. So we do a little trick. We start from x is equal to 1 to avoid that. X is equal to 1 up to infinity. X lambda raised to x over x factorial. We can't, this one goes here 1, x goes into x factorial how many times? X minus 1 factorial. Did you know that? But now, the power of lambda must also be the same as the denominator or the factorial. So what trick do we do here? This is e raised to power negative lambda, summation from x is equal to 1 up to infinity. Now I want to make this one lambda x minus 1. So if I factor out lambda here, I will remain what? Lambda x minus 1. Lots of indices. Are you seeing that? Over x minus 1 factorial. And you see, you can also factor out lambda here. So this is e raised to power negative lambda dot lambda. Then summation from x is equal to 1 up to infinity. Lambda raised to power x minus 1 over x minus 1 factorial. Now you can see, you can clearly see here that the power of lambda is the same as what is there in the factorial. So it forms, it's now easy or possible to express this as a series, as an exponential series. This is e raised to negative lambda dot lambda. This one as an exponential series converges at e raised to power lambda. So this one will be e raised to power negative lambda, e raised to power 0 dot lambda, which is equal to lambda, as required by the proof. So with this, we have verified that the expectation of a Poisson distribution is equal to lambda. That the variance of x is equal to lambda. The variance of a Poisson distribution is equal to lambda. How do we do this? We start by expressing the formula for variance. Var of x is equal to expectation of x squared minus expectation of x. the whole of this square. That is the variance. Already we have this, isn't it? We have this. So it means we have expectation of x squared minus lambda squared. Because this one we have proved that the expectation of a horizontal distribution is equal to lambda from our previous lecture, or our previous video. Yes. Now let's look at the expectation of x squared. Let's deal with this. We can call this one equation 1. Equation 1. Now expectation of x squared will be summation from x is equal to 1. We cannot sum from 0 again. Because if we sum from 0, everything will boil down to 0. Because of the existence of x squared here. Up to infinity, x squared summation, e raised to power negative lambda raised to power x over x factorial. Again, e raised to power negative lambda is not a function of x. So we factor it out. E raised to power negative lambda summation from x is equal to 1 up to infinity x squared lambda raised to power x over x factorial. We can divide. This one is e raised to power negative lambda summation from x is equal to 1 up to infinity x over x minus 1 factorial. I've divided this x and this x. They are like terms. And again, I can factor out lambda into lambda x minus 1. Same trick we used when we were getting the valid PNF. So this one you have e raised to negative lambda summation from x is equal to 1 up to infinity. Now we can let y be equal to x minus 1. We can do this by change of variables. If we let y to be x minus 1, it means x is equal to y plus 1. True or false? True. So whenever we find x, we put y plus 1. Summation of y plus 1 into brackets lambda raised to power y now. This one is now y because we have replaced it here. Yes. Yes. Over y factorial. Of course, this now y, now we are summing from y is equal to 0. From y is equal to 0 because we don't have y. Oh, this one will not boil down to 0. Now, but we know the expectation of x, isn't it? X is a horizontal random variable. We know its expectation, which is equal to lambda. If that random variable is also y, we can tell its expectation to be lambda. And therefore, here we have e raised to negative lambda plus 1 into lambda summation from x is equal to 0 up to, not x but y is equal to 0 up to infinity lambda raised to power y over y factorial. You can see this one is also exponential series. So you have e raised to negative lambda into bracket lambda plus 1 dot lambda into e raised to power lambda. This one and this one will cancel out because it will be e raised to power 0, which is equal to 1. And therefore you have lambda plus lambda squared plus plus lambda. You can call it equation 2. Now we substitute equation 2 into equation 1. Instead of writing expression of x squared, we write the equation 2. So we have lambda squared plus lambda minus lambda squared. You can see this one cancelled out is equal to lambda, as required by the proof. Therefore, the variance of a Poisson distribution is equal to example. Now consider the number of arrivals of customers in a bank. Suppose clients arrive at a bank or in a bank at an average of 2 clients per minute, at an average of 2 clients per minute. Determine the probability that from 1 no client will arrive in a minute. No client will arrive in a minute. Now solution to this problem. Remember the PMF is given by Px is equal to x, which is equal to e raised by negative lambda raised by x over x factorial, where x takes this value 0, 1, 2, all the way up to n. 0 elsewhere. What does this show? The probability that no client will arrive in a minute. Remember, x is the event of interest. X is the client. The arrival of the client. What is the probability that there will be no client arriving within 1 minute? Now you can see here that x will be equal to 0. And this is now the probability of x is equal to 0. We know lambda from this question. Clients arrive in a bank at an average of 2 clients per minute. That one tells you it is a Poisson distribution. It is not an exponential distribution. Because in exponential distribution, there is some intervals. After some interval, there will be arrival. But this one is Poisson. So lambda is equal to 2. Now you substitute the formula. Now you have e. The probability of e raised to power negative lambda is negative 2. Lambda raised by x. Lambda is 2. 2 raised by x. X is the event of interest, which at this point is 0. Over 0 factorial. So this is e raised by negative 2 over 1. E raised by negative 2. It is equal to, that's the probability. Exactly 2 clients will arrive. Exactly 2 clients. Same technique. Lambda, we are given the rate. The average rate is 2. Here the event of interest, x takes 2 clients. And PMF is e raised by negative lambda raised by x over x factorial. So we substitute e raised power negative 2, then lambda is 2 raised to power 2 over 2 factorial. Can you use calculator to solve that as well? Use the first one, you multiply by negative 2. But what I want you to do, not less than, at most 3 clients will arrive at the bank. At most 3 clients will arrive at the bank. And I can give you a hint. The hint is here. This probability of x can be 0, isn't it? Or px can be 1. One person may arrive, no person may arrive, one person may arrive, or px, 2 people may arrive, px, 3 people may arrive.